So here's the course. We all know and love what the course is. Let's quickly check out our calendar for this month. All right, we're on to December 8th. This is the last day of new content. We're finishing up section 5.3, which then finishes chapter 5. We're specifically going to be talking about independence today, you know, how to determine independence and then how to use knowing that something is independent or two events are independent in calculating probabilities. We'll have one more discussion board, which I'll talk about at the end of class. And that's it, right? We'll do a review for chapter 5 on Thursday. Yeah, and then I'll see you again on Tuesday for our traditional schedule. And then I will see you on Thursday for the final. And again, the day of the final, everyone needs to check into class. If you have already submitted all your self-assessments and you are happy with your grade, right, then you'll be able to just check out of class, be done with your first final for the day, and prepare for your fourth period final, whatever you need to do for that. If you have not finished your self-assessments, then you'll be expected to stay in the class until they're submitted. And I've confirmed that they're submitted. And the other option is if you have submitted everything, like all your self-assessments, but you'd like to resubmit some assignments or submit other missing assignments, you can stay logged into class and get those things turned in, and get feedback or get help on those assignments as you need them, as I'll be logged into the class as well. Just a quick review on what we've decided to do for the final. Yeah. We were down to the bitter end here, guys. We got, I'll see you 3 more times besides today for this semester, and then it'll be January the next time I see you. All right. Any questions about the last couple weeks? All right. The main goal of our day of the final is to make sure that everyone in this class passes the class. All right. That is the main goal. We're going to get enough stuff turned in and enough credit for things that you will pass. All right. And passing, we're looking for a C or better because that meets the requirements of CSU eligibility for your fourth year math class. It counts, right? So we want to shoot for that C or better. All right. So then, if we look at our module for this week, just want to point out in the live class resources, there are some extra videos, right? We have some work examples that are related to today's lesson, as well as one AP Daily video that relates to today's lesson about determining if events are independent and calculating probabilities for independent events. So there are some extra resources for today, so please don't forget about those. And then we're going to jump on into here. So it is Tuesday, December 8th, 2020. We're completing section 5.3 on condition, probability, and independence, specifically talking about independence, right? What is independence? Screen in order, there we go. All right. So first, before we get into our new content, some reminders. So the last day of new content. Thursday's class will be review. All assignments are posted. Today's discussion board is the last new assignment for the semester. Okay. In the chapter 5, self-assessment, right? The free response portion is a file upload submission. If you are taking pictures of your work that you've done by hand, and there is more than one page, right, you should add your pictures to a Word or Google Doc or save them into a single file somehow. for the submission, right? The submission area on the file upload only allows one file to be attached, okay? If you have multiple pages, right, and they're separate files each page, you're going to want to just put those into a document somehow where all of them are visible and upload that single document as your file upload. The other option, like if you can scan the documents, scan your pictures with your phone, like there's some free like apps that you can get for your phone that scan documents, and you can scan multiple pages and have that save as a single file. That's also an option, right? However, it will only accept a single file as the upload. You can't do multiple files. So please keep that in mind. I have had some students already turn in the Chapter 5 self-assessment. Of those self-assessments, had the same error as to answer some of the questions. So hopefully if you have already turned this in, you get some extra information today that allows you to make corrections if that's something you want to do. So, the last thing I don't want to forget to mention, the discussion board from Thursday last week. There was a very common mistake here with our tree diagram stuff. Some of you guys in your tree diagrams and in your calculations introduced a third option for the type of computer device being made. For some reason, some of you introduced a tablet as an option. So each state was producing laptops, desktops, and tablets. This is not an option. It's not part of the question. And many of you guys who included tablets decided to omit New York as one of the states. So I don't know if this is because maybe you didn't know what to do and you Googled the first part of the question and you got that result. All right. Make sure the result you find matches the thing you're actually looking for. In your tree diagram from the start, which in this case would be the distribution center, there are 3 branches, California, Texas, and New York. Each of those 3 branches has 2 branches, laptops and desktops. Okay? Please be careful. Don't introduce things that were not part of the question originally, and don't omit things that were part of the question originally. Okay, so I'm going to mention that. There's a very common error in the 20 responses that I've gotten for this so far. All right, please be careful and be mindful of what's being asked. All right, there's that too. Forget that. For now. Jump back in here. All right. So now, what is independence? This is the main topic for today. So we have a couple of scenarios here we're going to consider. First is tossing a fair coin. We've seen this example, right? We also have a pierced ears example. This is the same example we've been using throughout the chapter, where we have the statistics class that took data about gender and whether or not they had pierced ears. Yeah, so this one's going to use some of that data. When tossing a fair coin, the probability of getting a heads first, event A, and the probability of getting a tails second, event B, are both 0.5. Right? You toss a coin once, you have a 50-50 chance of getting heads. Toss it a second time, you still have a 50-50 chance of getting heads or tails. Right? The chances of first tossing a head and then getting a tails on the second toss can be given as follows. Right? You have the probability of getting a tails, given the first toss was a heads, is the same as the probability of getting a heads then a tails. Right? Heads and tails in 2 tosses, divided by the probability of getting a heads, which is 0.5 times 0.5 divided by 0.5, which gives us 0.5. The probability of the second toss does not change despite knowing what happened on the first toss. And again, this kind of goes back to the fact that a coin doesn't care. It doesn't know it's been tossed before. It doesn't know it's getting tossed right now. It just lands in its heads or tails. Right? Knowing what already happened has no effect on what's happening next. In our pierced ears example, right, the two events were A, student is male, and B, student has pierced ears. We know the following. These are our probabilities that we've already determined in our previous examples. Probability the student is male is 90 out of 178 students. Probability the student has pierced ears is 103 out of 178. And the probability that a student has pierced ears given that they're male, so given that we already know that the student is male, is 19 out of 90. All right. Knowing that a student is male changes the probability that the student has pierced ears. So if I already know one outcome, which is the student is male, that changes the probability of me having a student with pierced ears from the original probability from the whole class, right? We can see this because the probability of the student having pierced ears given that they're male is 19 over 90, which is not equal 103 over 178, which is the probability that the student has pierced ears. All right. So once I know some of the information, my probability changes. This is the basis of independence. Whether or not knowing something changes the likelihood of the next outcome, which is what we will define now. When knowledge that one event has happened does not change the likelihood that another event will happen, then the two events are independent. And we get the textbook definition. Independent events. The events A and B are independent if the occurrence of one event does not change the probability that the other event will happen. In other words, events A and B are independent if probability A given B is equal to the probability of A and probability of B given A is equal to the probability of B. Okay. Now, something important that I want to point out is in our the second statement in here, right? Events A and B are independent if probability A given B is equal to probability A and probability of B given A is equal to probability of B, right? If you guys remember back to Math 3, we had statements, conditional statements. They were if-then statements. If this set of things happens, then this is the conclusion, all right? This definition is an if-then statement. It says, if both of these equations are true, right? Both must be true, that's the and, then the events are independent. Okay? We can only say events are independent if both of these equations are true. If one is true, but the other one is not independent. Okay? Both must work. All right? Both of these equations must be true. Okay? Otherwise, not independent. Again, that's the significance of the and linking these two things within the statement. Okay. Does anyone need a moment to write down the definition or anything else from this slide? I do highly recommend that you have this definition. Okay. Is there anything I can clarify so far? Okay. So then, let's look at an example of how to determine independence. In this example, We have 452 high school students who completed a survey were randomly selected. The survey was trying to determine if there is a relationship between gender and relative finger length. The two-way table below shows the gender of each student and which finger was longer on their left hand, index finger or ring finger. All right, so we have index finger longer, ring finger longer, same length, female, male. We have our two-way table. Okay, so this is going to be the basis of our example. And we're trying to answer, are the events female and has a longer ring finger independent? Let's see if my pen cooperates more than it did just earlier. So we need to check two possibilities, right? Based on our definition for things to be independent. Let's first, we're going to call female, being female in event A, has a longer ring finger, event B, to make it so we can write this stuff down a little easier. And we need to determine, is the probability of A given B equal to the probability of A? And then we need to check, is the probability of B given A equal to the probability of B? And putting a little question mark above the equal sign is essentially telling the reader or telling someone else that I'm checking to see if this is true. I'm not saying these are equal yet. I'm testing it. And this is because when you get into higher level maths and college level maths and things, you can't just put things equal to each other because you want to. They must be equal, or you need to have some sort of notation saying that I think they might be, so I'm going to test. Right? And that's what the little question mark does. Right? So now, let's write down what we know. What can we fill in about our probabilities? Right? First, probability of A. Right? We can use the two-way table to get this. And the probability of A says, okay, what's the probability that a student in this sample is female? We have 212 female students out of 452. Right? And the probability of event B, right, students having a longer ring finger. Right, so this is our ring finger being longer. That's 234 out of 452. All right, so those are the easier ones to find. Next, let's find the probability of A given B. Right? So essentially, what is the probability that the student is female given they have a longer ring finger? Okay, that's the probability of A given B. That's equivalent to the intersection of A and B divided by probability of B. So the intersection, right, probability of A and B, right, is ring finger and female. So we have 82 out of 234, right? No, sorry. This is out of 452. That's the intersection. And then probability of B, 200 out of 452. Right? Which is equal to 82 out of 234. So now we have the first thing to test. Is the probability of A given B equivalent to the probability of A? Well, in decimal form, 82 out of 234 is 0.35 about. All right. Probability of A, 212 divided by 452 is 0.469. These are not equivalent. So that means we're done. We don't need to test the other one. It's unnecessary because this one failed. Which then gives us our results. Yeah. Right. Pardon me. Oh. The events pen are not independent. Right? And it's because the test failed. Right? Probability of A given B has to be equal to the probability of A for the first part to even move forward. So it did not meet the conditions of the definition, so we do not have independent events. Is there anything I can clarify about this example or anything I can explain further? Does anyone need a moment to write anything down from this example? Okie dokie. Then we have a multiplication rule for independent events. Right? We already have the general multiplication rule. That is this first part. When events A and B are independent, probability of B given A is equal to the probability of B. It's in our definition. So if I know events are independent, right, we can simplify the general multiplication rule by substituting the probability of B given A with probability of B. And we're left with just probability of A times probability of B. This only works if you know the events are independent. Otherwise, you should use this rule because probability of B given A is not going to be the same as probability of B. Right? And so we have the textbook definition, multiplication rule for independent events. If A and B are independent events, then the probability that A and B both occur is probability of A and B is equal to probability of A times probability of B. Okay. Anyone need a moment to write this down? Please raise your hand. Okie dokie. All right, so now we're going to do an example. Right? In baseball, a perfect game is when a pitcher doesn't allow any hitters to reach base in all 9 innings. Historically, pitchers throw a perfect inning, an inning where no hitters reach base, about 40% of the time. So to throw a perfect game, a pitcher needs to have 9 perfect innings in a row. We want to answer what is the probability that a pitcher throws 9 perfect innings in a row, assuming the pitcher's performance in an inning is independent of his performance in other innings. Okay? So let's look at this example. We're going to really work in OneNote just because my pen works better in OneNote, and I'm going to be doing more writing for this example. So, all right. So for this example, I'm trying to find out what's the probability of a perfect game. which is equal to the probability of getting 9 perfect innings in a row. Right? Getting 9 perfect innings in a row is the same as getting 1 perfect inning and a second perfect inning, so on and so forth. 9th inning in a row, right? Based on our new rule, assuming that these are independent events as we've been told to do, and we get to assume that these are independent things, is equivalent to the probability of getting 1 perfect inning times 2 perfect innings, all the way through to the 9th perfect inning. Each of these has the probability of 0.4. That was the given information. We have a 40% chance of throwing a perfect inning. So having our first inning be perfect, we have a 0.4% chance, 0.4 probability. Getting the second inning, because it's an independent event, also has a 0.4. That's 0.4. Right? And this would continue times 0.4. This happens 9 times, which is equal to 0.4 to the 9th, which is then equal to, looking at my notes, a really teeny tiny number, 0.00026, approximately. So there's less than a 0.5% chance any given game that the pitcher throws a perfect game. All right. So there's our probability. Okay. We have a probability of 0.00026 chance that the pitcher throws 9 perfect innings in a row. And again, this problem is solved based on the assumption that each inning pitched is an independent event. So we get to reuse that 40% chance each time. All right. Any questions about this example? Does anyone need a moment to write anything down from this example? All right. So then here's another type of problem we can solve using our multiplication rule for independent events. This one's a little bit more complicated. All right. The first trimester screen is a non-invasive test given during the first trimester of pregnancy to determine if there are specific chromosomal or abnormalities in the fetus. According to a study published in the New England Journal of Medicine, in November 2005, approximately 5% of normal pregnancies will receive a positive result. If 100 women with normal pregnancies are tested with the first trimester screen, what is the probability that at least one woman will receive a positive result? Okay. So this involves a little bit more moving parts. right? So in this problem, we're looking at a 5% chance, 5% chance of a positive result. Okay, this is probability-wise 0.05. It's easier just to convert this to a decimal. The decimal is usable in our calculator, and it works out much better. So we have 0.05 is the probability of a positive test. Right? Anytime a test is given. Right? We want to find the probability of at least one positive test out of 100. All right. So the problem with this right away is that I'm looking at least one. That means I can have one positive test out of 100, and that counts. I could have 2, I could have 3, I can have 4, I can have 5, I can have 6, all the way up to 100 positive tests, right? So if I want to like kind of straightforward calculate this probability, I need to find what's the probability of getting only 1 out of 100 positive tests. And then what's the probability of getting 2 out of 100? What's the probability of getting 3 out of 100? And add all of those probabilities up, okay? Unfortunately, that's a lot of calculations, right? Just to find out the probability that we get 1 positive test out of 100, there's 100 ways to get 1 positive test, right? So we think of some of the problems we've done when there's multiple routes to get a result, we have to add all of those together to get the final probability. So that means just to find out the probability of getting 1 positive test out of 100, right? We have to do 100 calculations. That's not reasonable. You can't do this. This would take too much time to do by hand, right? So what we do, we think outside the box a little bit and say, hey, this is going to be overwhelming. This is going to be too much stuff. However, this is the same as the complement, 1 minus the probability of no positive tests. All right? Because if I have at least 1, the complement is getting none. So the probability of at least 1 positive test is equal to the probability, is equal to 1 minus the probability of getting no positive tests out of 100. This is going to be easier to manage, all right? Because these are independent events. We know this because knowing what one person tested, what one person's results are on the screen, doesn't indicate what the next person's result will be, right? They're entirely different people, right? The test doesn't know that it just tested someone else, right? So these are independent events, right? So that means moving forward now we can say, okay, well, what's the probability that a single test comes back negative, right? So the probability of a negative test, meaning the even test, is equal to 1 minus probability of a positive test, which is equal to 1 minus 0.05, which gives us the probability of 0.95. So in a single test, right, we're just looking at a single time, one woman getting this test done, there is a 95% chance that the test will come back negative. Okay? So to get 100 the probability of getting no positive tests out of 100 is the probability of getting 100 consecutive negative tests. And now this is starting to look like the previous problem. All right. So we can move on to the probability of no positive test of 100 equal to the probability of 100 consecutive negative tests which is then, these are independent events, probability of getting negative test times negative test times negative test times negative test, right? And we get 0.95 times 0.95, 0.95, 100 times. We would need this outcome to happen 100 times in a row in order to get no positive test, right? This results in 0.95 to the 100th power, right? Which is 0.0059. Right? So the probability of getting 100 consecutive negative tests is 0.0059. So that means now this number goes in here, right? And we get 1 minus 0.0059, which equals 0.9941. Right? This is the probability of at least one positive test out of 100. This math we can do. We can doing the other, trying to do it straightforward, that would take way too long. So then we finally can say there's over a 99% chance of getting at least one positive test out of 100. Okay. What questions do you have? This example is a little more complex. Is there anything I can clarify? Okay. This work will be added to our PowerPoint slides, so it will be there if you would like to see it again later. One of the last things I want to go over here is the fact that mutually exclusive is not the same as independent. All right? Two mutually exclusive events can never be independent, because if one event happens, the other event is guaranteed not to happen. So essentially, when you have mutually exclusive events, it will never be, those two events cannot be independent. They must be not independent or dependent, right? Knowing that one of those two disjoint events happens guarantees the other one did not happen, which changes likelihood, all right? And that's what my statement here says. So knowing one event has occurred changes the likelihood the other one occurs. Let's consider these two events. event A, the person is male, and event B, the person is pregnant. These events are mutually exclusive. The person can't be both male and pregnant. However, if we know the person is male, the chance of them being pregnant is 0. Right? We also get that the probability of B given A is not equal to the probability of B. Right? So the events are not independent. Right? These two concepts seem like they could go together very well, but they do not. They are different things. Right? So in a couple of the Chapter 5 self-assessments that were submitted already, some students thought that the questions asking about independence were asking about if the events were being mutually exclusive. It is not. Independence is a different concept. So please be careful. All right. Does anyone need a moment to write anything down from this page? Thus concludes Chapter 5, Probability. All right, we covered randomness, probability and simulation, probability rules, conditional probability, and independence. All right, Thursday will be a review. And then the last thing I want to look at, calendar, is the last discussion board. All right, you're in the first question here, you're given 3 scenarios. You need to determine whether the events are independent. Some of them you might be able to logically reason out. Some of them you're going to need to do the math. All right. There is a second question. Please don't forget about the second question. You will be using the multiplication, the general multiplication, the multiplication rule for independent events. Big mouthful. For question 2. All right. Don't skip question 2. Is there anything else I can clarify for you or answer for you? And if there is not, you guys are free to go. That's the entirety of the lesson. I've covered everything I want to cover for today. If you do have some questions, please feel free to stick around and get some help.